Okay, so in this video, we're going to talk about intermolecular forces. So intermolecular forces are attractive forces between molecules. So we've been talking a lot about, for example, how polar molecules are really attracted to other polar molecules. Those attractions are caused by intermolecular forces. So we're going to give a name to those attractions, basically. Now I want to make it clear, these are between like two separate molecules. So, for example, here's a molecule, and if I had another molecule of this type, an intermolecular force would be an attraction between this molecule and a separate molecule. So, there are three types of intermolecular forces. The first one we're going to talk about is called London dispersion forces. It's kind of a long, complicated name, and it's a weak force. It's a pretty weak intermolecular force, but it's found in every single type of molecule. So it's found in nonpolar molecules and polar molecules. And we're going to show what one looks like. So we're going to draw a nonpolar molecule, because although these forces are in both, they matter more for nonpolar molecules. So here's two chlorine molecules. To show the intermolecular force, the attraction between them, we can draw kind of like a dashed line. Now notice these don't have any charges, these chlorine molecules, so this force is not very strong. And you might be wondering, how does this force even exist? Why are they even attracted if there's no charges? And I'll try and explain the answer. It's a little bit complicated, but we draw these electrons as stationary, like they're not moving. But really, these electrons are kind of moving around the molecule all the time. So you can imagine there might be a point in time where for this molecule, there's more electrons over here, giving it a slightly negative charge on this side. And for this molecule, maybe more of the electrons are over here, giving this side a slightly positive charge. And for that moment, these two molecules are then attracted. But it's a very weak attraction. Think of it as like a really, really short-lived crush. Like, it lasts like a day. I mean, for these molecules, it lasts like mere seconds, but a short-lived crush might last for a couple days. So, London dispersion, very, very weak forces. The next type of force is called dipole. So you remember that, or maybe you remember, that polar molecules have these things called dipoles that kind of show which atom is electronegative, and so like which one is partially negative. And of course that means that the polar molecules are attracted to each other. So every single polar molecule will have dipole-dipole forces. And these are pretty strong. We're going to call them medium strength. I'm going to give you an example of one. So HCl is a polar molecule, right? It's not symmetric. And the Cl is going to be the negative side, the partially negative side. The H is the partially positive. We'll draw another molecule here. Label the charges again. And then the negative side and the positive side are attracted. Now, since these charges are always here, this attraction is much stronger than the London dispersion. So this is like a really intense crush, or maybe like a casual relationship or something, that attraction. Okay, the last type of force is called hydrogen bonding, and you might have heard of this before. It's kind of confusing that we call it hydrogen bonding because it's not really a bond, it's just an attractive force. But it is found in certain types of polar molecules. So it's specifically polar molecules where, or with these three specific bonds, either H bonded to F, H bonded to O, or H bonded to N. So you can remember F-O-N, like fawn. Now hydrogen bonds are really, really strong. And that's because when you have these bonds, these are really strong dipoles, like the oxygen is very negative and the hydrogen is very positive. So water has hydrogen bonding, And you might remember from some of the labs that we've been doing that hydrogen is like very, very polar. And when we say that it's like very, very polar, it's got really strong attractions, it's because of this hydrogen bonding. So here's one water molecule, here's another one. And here's the negative and the positive side. And so this right here is the hydrogen bond. These are the intermolecular forces. Okay, so the hydrogen bond is not this bond, it is this attraction right here. All right, but hydrogen bonding is only in polar molecules with HF, HO, or HN. All right, back to London dispersion forces. If molecules are bigger, they're going to have bigger London dispersion forces. So, for example, if we have a molecule like C10H22, it's a big, just like hydrocarbon, it's going to have stronger London dispersion forces than CH4, for example. So same elements, but different numbers. Methane is a gas, and the reason it's a gas is because it has such weak London dispersion forces. They like don't even really matter. Okay, so a couple things that happen because of intermolecular forces. Weaker intermolecular forces are going to cause you to have a lower melting point, a lower boiling point, a lower solubility in water, and lower surface tension. So again, gases have low melting and boiling points because they only have London dispersion forces that are really weak. Oil doesn't have very much surface tension because it only has London dispersion forces. But it's a bigger molecule, so it's a liquid at least, but still low surface tension compared to like water. Stronger intermolecular forces are going to be the opposite of all this. So they're going to have a high melting point, so like solids and liquids have stronger intermolecular forces. They'll have a high boiling point. They'll be more soluble in water. And they'll have higher surface tension. Okay, so just to summarize, if you're a nonpolar molecule, the only intermolecular forces that you experience are London dispersion forces. So just those weak forces. Polar molecules, however, are going to experience both, because notice polar molecules are in London and, London are in polar, and dipole-dipole are also in polar. So polar molecules have both London dispersion and dipole-dipole. And then if you are a polar molecule with specifically HF, HO, or HN, then you're going to have all three. London dispersion, dipole-dipole, and hydrogen bonding. So what you're going to have to be able to do after today, just so you know, is look at a molecule. So I'm going to give you two examples here, and figure out what types of intermolecular forces it has. So to be able to do that, you're going to have to figure out whether it's polar or nonpolar. So this one, it's symmetric this way, but not this way, so that means it's polar. So automatically, that already means it's going to have London dispersion and dipole-dipole. And then to figure out if it has hydrogen bonding, I have to look and see if it has H bonded to N or F, and it does. So this one's actually going to have hydrogen bonding. I'm just going to abbreviate that as H bonding. Let's look at another one. Let's look at like CH4. This one's symmetric in both directions, so it's nonpolar. So it's just going to have London dispersion. So if it's nonpolar, it's always just going to be London dispersion. If it's polar, it's going to be London dispersion and dipole-dipole, and then maybe, if it's got H bonded to N over F, hydrogen bonding. So I know it's a little bit complex, but I think you guys can do it, and I think this stuff is cool because it explains a lot of things that we see in the world, like why things are gases or solids or liquids. It's because of these intermolecular forces.